Dr. James Leslie and Dr. Laura Parker at McMaster University. Today I'll be talking about a study of jellyfish galaxy tails in a simulated galaxy group. So as a reminder what a jellyfish galaxy is, these are essentially galaxies that exhibit these long gaseous tails that you can see in this image over here. And they're generally found in really dense galactic media, such as in clusters and groups, etc. And the simulation I'm studying is ran using gasoline 2. It is a high-resolution zoom-in simulation of a large box that has high resolution at redshift 0 up to about 3 real radii. So studies on jellyfish galaxies has been done before in simulations, but mostly in isolated galaxies and using wind tunnels to simulate like ground pressure and stuff. So the benefit of studying in a group simulation is that we're able to study these jellyfish galaxies in a quote unquote actual like galactic environment as opposed to like a wind tunnel. So the first thing we want to do is identify these tails, which is we've done here. So the tails are identified using an algorithm based on a series of like velocity and temperature cuts. I won't be going over that. If you're interested, you can speak to me later. But they exhibit some interesting properties. So the first thing is that the tail gas is often dense. So between the disk and the virial radius, the densest gas is often the tail gas, as you can see in the top left. And then the top right, I've also highlighted the tail particles in line. Another interesting property is that if you look at the velocity map in the bottom left, you can see that the flow is looks largely laminar and parallel around the galaxy, but in the wake of the tail itself, you can see there's a lot of turbulence going on. And that is strongly suggestive that there could be some turbulent mixing processes going on there. And finally, if you look at the bottom right, you can see the temperature map. And not only is the tail itself, generally cooler than the surrounding CGM/group medium, but if you look really closely, you can see sort of if you look around, you can also sort of see what looks to be like a bow shock in here in dark red. So the next question is to ask, where did the tail gas come from? So up here, what I've done is I've highlighted two distinct groups of gas. In green, you have the gas that came from the disk, and in black, you have the gas that never entered the disk. So the surprising thing is that a significant chunk of the tail gas never came from the disk. And if you look back in time, you can see where this gas came from. You can see most of the green particles came from the disk itself, but most of the black particles are nowhere to be found. So that strongly suggests that a lot of the tail is actually material that was entrained from the group medium. And then it is likely entrained through some turbulent mixing processes due to this turbulence that we see down here in the velocity map. And then I'm out of time. So anyways, that's my talk. If you're interested, come speak to me if you have more questions. Thank you.
Thanks, Alex. We are then going to switch to remote, and Vita will be up next.
Yes, thank you. Okay, can you hear me?
Yep.
Okay. Hello, everyone. My name is Vida Saidzadeh. I'm a PhD candidate at the University of Victoria, working with Arif Babul. My research focus is studying the multi-phase structure of the circumgalactic medium around massive central galaxies. The observations from the BCGs in the cool core clusters showing that the gas surrounding these galaxies has a multi-phase structure. As you can see in the picture to the right, the cold 10 to the 4 Kelvin gas filaments, which have been shown in red, coexist with hot green X-ray emitting gas with temperature about 10 to the 6 Kelvin or more. The nature of this multi-phase CGM gas is not yet fully understood. So there are a lot of open questions like where this cold gas came from, how they evolved, and what is their fate. So here is where the simulations comes to play a role. Although seeing the multi-phase structure of the CGM is not easy in cosmological simulations because of the limitation of the resolution, the recent improvement in resolutions in these kind of situations give us the opportunity to see the multi-phase structure of the CGM. In our analysis, we are using Romulus sets of simulations where in their high resolutions give us the chance to see and study the cold phase of the CGM around BCGs. Our results shows that the gas in the CGM cools in two modes: the cooling flow, the gas that is getting closer to the center of the group and cools, and the other mode is the gas that is cooling through the perturbations. It's the gas got perturbed. If it's thermally unstable, it cools very fast and precipitate. So the next natural question that comes in mind is that, so what drives these perturbations? The result of the studying the idealized simulations shows that the turbulence that caused by jets are the main source of these perturbations. But the question is that if we look at the cosmological simulations and if we take to the account the effect of more physical processes that happens around the galaxy, is the result will change? And the answer is, from our results, looking at the Romulus cosmological simulation, is that we see that the dominant source of the perturbations around the BCGs is actually coming from the structures and structure wakes. So if you are interested to know more about in more detail about this work, please see Arif's talk in the upcoming session, or feel free to ask me questions. Thank you.
Okay, thank you, Vida. Next flash talk will be Christian Casey.
Can you see my presentation?
Yes, we can.
Great. Okay, so I'm Kirsten. I'm going to be talking about a backslash galaxy candidate near the M81 group. A backslash galaxy is basically just a galaxy that has fallen into the virial radius of a host and since exited. The galaxy that I'll be talking about is this one. Informally called it Blobby. In projection, it lies about 1 virial radii from the M81 group. And to measure or to establish it as a backslash galaxy candidate, we measure the surface brightness fluctuation distance, which basically just takes advantage of the fact that stellar populations that are further away from us have a smaller variation in brightness between pixels in your image. We can measure that variation to get a distance, and when we do that, we get that Blobby lies between 1 and 2 virial radii from M81. It has a stellar mass about 10 to the 7 solar masses, and its red color suggests that it's quenched. Now, the reason this is important is because the star formation of galaxies in this mass regime can be affected significantly by the environment that they're in. So field galaxies in this mass regime are predominantly star forming, but satellite galaxies in this mass regime are much more likely to be quenched. Now, backslash galaxies often resemble satellite galaxies more than field galaxies, and we use this and the fact that, and the distance measurement that we get to argue that Blobby is likely backsplash. Now, we would like to know more about how, why, and on what time scales galaxies like Blobby are quenched. And for that, we turn to simulations. So for example, Applebaum et al. Simulated Milky Way-like hosts, which are smaller than M81, but they found several backslash galaxies in their simulation. I circled this region where Blobby lies, and I just like to point out that based on the magnitude, Blobby is brighter than their simulated backslash galaxies, which likely means that its stellar mass is higher than those galaxies. On the other hand, other groups have simulated larger halos, so mostly group halos and cluster halos, and found many backslash galaxies. I've marked where M81 is in this plot, and only a couple of backslash galaxies are simulated in this host mass range, and you can tell from the color bar over here that the masses of these backslash galaxies are larger than Blobby. So Blobby really just demonstrates the need to simulate backslash galaxies at more intermediate masses and around a wider range of host halos, not just Milky Way or large groups or clusters, in order to understand how those environments are impacting the star formation of galaxies like Blobby. Thank you.
Thank you. And the last speaker before we take questions is Alex Pettit.
Hello there, everybody. I'm assuming you can all see my screen. If not, I'm going to hear a shout if it's all going wrong. My name's Alex. I'm going to quickly talk to you about a project we've got going at the moment called Bespoke, collaboration with a few people who've already spoken here before today, as well as Sam Benincasa and Elizabeth Isles. And the idea of this project is that when people do numerical simulations of galaxies, they love to bandy around the phrase, this is a Milky Way-like galaxy, right? I'm sure you've all heard of this phrase several times before, but the reality is disk galaxies that are nearby to us all have little nuances and intricacies that make them a little bit special, a bit different. We have a wealth of information about their stellar surface density profiles, how much molecular gas is in them, where the atomic gas is. And as a result, they all show slightly different nuances as to how they're going to form stars. So their tracks, each one of these galaxies follows along this Kennecker-Schmidt relationship between gas mass and how much stars it's forming is kind of different for each one. They all have subtle nuances and changes. So the idea here is we're trying to simulate a bunch of specific nearby galaxies. We're concentrating on disks and trying to understand what makes them tick. How does their global structure, their surface density, their rotation curve, their mass profile, how much gas they have, etc., inform their inner workings of how they're going to evolve and change and how they're going to form stars. So it wouldn't be a simulator without showing you a pretty movie. This is one of our disks. On the right, I've got the atomic gas mass in this galaxy, and on the left is just a mock optical image of the thing. And we have a few of these now. We're working on paper one, trying to dissect why the star formation might be different in 3 specific galaxies that we've looked at. We have a bunch in the can at the moment. My PhD student has worked on the 2 on the left here, NGC 4303 and 3627, which are 2 nearby bars. Her paper, Isles et al., is out at the moment. The second one is in prep. And 2 on the right are kind of part of the flagship Bespoke paper studying a few nearby disks. We have a barred disk and a kind of edge-on-y, spiral-y sort of thing. And there's another one as well, but I don't want to overload you with too many NGC numbers. So the kind of science we're looking at in the first round is we've got very simple physics in there. We've got Ben's lovely super bubble feedback, and we've got some cooling, and that's about it. And we want to see how that affects how the galaxy is going to form stars, in a sense. Looking at things such as how the shear rate is changing how gas is going to accumulate into star-forming particles, how the different velocity fields are affecting the motion of the gas, and looking at, for example, how the star formation efficiency might change as a function of radius between each of the disks. And we see some kind of interesting things. First of all, like they all tend to have a little bit of a difference in their star formation efficiency with radius. And we reproduce this to an okay extent. Simulations on the right here and observations are on the left, but it's still quite a bit of a ways to go to split them apart to a much more larger size. And there's a few other things like this that work on at the moment. If anyone is interested, drop me a Slack. I lurk on the Embody Shop Slack a lot, but James is here as well. He's kind of like the advertiser for this in person. So thank you everybody for your time and attention.
Okay, thank you, Flash speakers. Do we have questions for our Flash speakers, either in the room or on Zoom? Why don't you go ahead, Andrew?
Hi, it's Andrew Ponson. This is, I think, a question for Alex Liu. It was really interesting to see the entrainment that you're seeing. Do you know how resolution dependent that is? Because I know, people like Freke van der Voort would probably argue that's super resolution dependent, what you're seeing.
Yeah, so that is something that me and James have actually talked about. We've talked about possibly rerunning one of these galaxies with either higher resolution. Unfortunately, we haven't gotten around to that yet. We haven't explored it that much yet. But so yes, right now we only have like this one resolution that shows this. But Yeah, it's something we're thinking about.
Okay, and Ben, I see you have a question. Why don't you go ahead and unmute and ask?
Yeah, this is for Alex Pettit. Excuse me, sorry. Oh, sorry, apologies. So as far as I know, Bespoke is essentially crafted initial conditions. They aren't cosmological galaxies that you've picked out to kind of somehow match real observed galaxies. For the ones that have things like strong tidal features, I assume you're also adding in some perturbers as well. Would you be able to talk a little bit in detail about how that works?
Yeah, good question. So a lot of these disks and these famous surveys have like tidal features, like a lot more than you expect. We've tried to, in the first round of targets for the IMPREP paper, we've got just isolated disks or things that look really isolated. Elizabeth's paper on NGC, the two barred ones, one of them is heavily tidally perturbed. So we set up a small companion in there and triggered a bar to form quite a bit earlier than I normally would have done. And we haven't tailored the orbit to be like specifically to what an orbit of a companion might be. We just wanted to generate a tidal response that looked about right. I did a few papers on tidal interactions a couple of years ago, so I kind of used that as kind of a stepping stone to set up something with a companion that came by and triggered a bar and arms that sort of looked the right way. If that answers your question.
Okay, I have a very quick question for Kirsten, and then we should probably move on. I've got a stupid theorist question, which is there any possibility of measuring a stellar velocity dispersion or any way of getting a handle on the dynamical mass of Blobby?
Yeah, well, so we don't have currently the observations necessary to get a stellar velocity dispersion. We'd need, spectra or something. Right now, we just have the photometric data from Large Binocular Telescope. In terms of getting a dynamical mass, I mean, the most we have right now is stellar halo mass relation. We would need, again, more observations of maybe globular clusters or, like you said, the velocity dispersion to get that. But right with the observations we have right now, we're not able to get those, more than just using stellar mass relation.
Okay, thank you.
Mhm.
All right, then let's thank the flash speakers one more time.
Good afternoon, everyone. And thank you so much to the organizers for inviting me. I'm very excited to share this work with everybody. I believe I'm using this. So today I'm going to talk to you about the circumgalactic medium. And specifically, I'm going to talk to you about the hot phase of the CGM. So many people in this room are familiar with the idea that when you have any sort of extended gaseous object, especially in a bound gravitational halo, it's inevitably going to show multi-phase structure, right? And also there's a lot of people in this room, especially the people in Seattle, who are familiar with a lot of the work on the CGM that was done using UV absorption studies, such as those by COS halos. And those trace a colder phase of the CGM, right? So there's extensive literature in that field, and I encourage you to read that. In fact, the first image I use in my talk is always from this paper by Tumlinson, Peoples, and Work, which are really the COS halos people. I think it's really beautiful because it just quickly gets you a sense for what we're talking about. So, so the CGM is defined as the gas that lives between the star-forming regions, so the ISM, so it's not the ISM, yeah, the CGM is not the ISM, and between that and between the virial radius of the galaxy. So that's what we call the circumgalactic medium. This is considered important because on the one hand, it's the interface between the galaxy and its large-scale environment. You could have gas that is accreted, right? So from the cosmic web, if it's in a group or cluster medium, then from there, it sits as this reservoir within the galaxy halo. It eventually is the source of the baryons. Actually, the bulk of, well, depending on your theoretical model, which is still evolving, we expect a significant chunk of the baryons in a galaxy to live in the CGM. Oh God, sorry. As stars form and undergo feedback, and there's an AGN in the middle, which also needs baryons to be fueled, you're going to experience all this activity between the stellar disk or ellipse and the CGM, right? So there are these feedback processes that cycle material between the ISM and the CGM. And so the CGM is actually holding signatures of the feedback processes that happen in the galaxy, okay? And it does this in a different way than other tracers. So for example, usually when you run a simulation of, especially a cosmological simulation of galaxy evolution, you tune your feedback models to make sure you reproduce properties of, for example, the stars. We want to reproduce the stellar mass distribution, star formation rates, et cetera, et cetera. But it also leaves very clear signatures on the CGM, especially this extended hot diffuse CGM. For example, Drummond Fielding had these simulations in 2016 where, if you do an idealized study, you can tweak one parameter of your feedback model at a time and see what it does, right? So in that particular paper looked at the mass loading factor of stellar winds. And he was like, if you change eta, you can end up with these profiles that are more or less cuspy, more or less cold or hot at the center, right? So you can see these signatures in idealized experiments. On the other hand, no feedback process operates in isolation, right? A realistic galaxy has all these feedback processes happening at the same time. And so in a cosmological simulation, you implement subgrid models that capture different ideas about how all these different feedback processes are working all together. You run the whole thing through, and then you look at the properties of the CGM, and then you compare that to observations, right? Now, at this conference, I'm obliged to answer why I did not use Romulus simulations for this. And I do apologize. But the simple, Thomas asked me this question to my face. And the answer is simply that nobody so far has prepared any X-ray mocks from the Romulus simulations. So if anybody is looking for a project, may I recommend? So at the moment that I started this paper, Ben Oppenheimer had already prepared detailed X-ray mocks from the TNG and Eagle simulations. And that is the simple reason why those are the ones that I was able to explore in this paper. Okay, and so in these simulations, you can look at various properties of the CGM as a function of things like galaxy stellar mass, galaxy star formation rate, things like that, right? So we start to get to a place where you can actually do a relatively apples-to-apples comparison between the simulations and observations. Now, why am I able to do this comparison now? So until last year, this was our best X-ray map of the sky. This is Rosat. It's it's about as old as me, and I have white hairs. And so, right? But as of last year, we suddenly had eRosita, right? Which has 30 times the sensitivity of Rosat, more than twice its spatial resolution. And so specifically, I have this, oh, sorry. Yeah, so for the first time, we have a map of the entire sky, which allows us to see a large collection of galaxies in the X-ray in a way that wasn't possible before. Okay, if you look at the literature, you'll see plenty of studies using Chandra, XMM, and so on that will identify usually giant elliptical galaxies that are close by, where you have a good chance of catching the CGM as an individual detection. And this is important because here's an image, okay, where the noise is 10 times large. Did I do that? 5 times larger than the signal, okay? I would be very impressed if you could see the signal. But what I'm going to keep doing now is I'm going to keep flashing a new image on the left every time. And on the right, I'll show you the cumulative image, okay? And so what happens is that the noise, because it is random, it cancels out as you keep adding more images. But the signal will accumulate, right? So this is what the process of stacking is all about. This has been done in the optical for a long time. It's also, yeah, it's been quite successful in the X-ray as well, right? So my hope is that we're gonna, but the thing with stacking is you can't just stack random cutouts from the map. You need to start with an educated guess about where to look. So first of all, the X-ray map that I have, so I showed you the full sky map of E Rosita. That's actually not fully publicly available yet. I was working with this test patch that's called EFEDS. It's the E Rosita Final Equatorial Depth Survey. This was data that was collected over the course of the first 3 months of the launch of E Rosita. And it's a relatively small patch of sky. It's 140 square degrees, so about 1/300th of the data that we will have in the future. But it was so designed that within 3 months, this patch achieved exactly as much depth as the whole survey will have at the end of 4 years, right? So it's as good as the survey will get, pretty much. And so this is really where you get to test out all your experimental ideas. Now, you have to know where to look. If I'm looking for the CGM, I need to know where the galaxies are. So I went to SDSS and picked out galaxies that were at a certain redshift range, stellar mass range that overlapped with EFEDS. I'll describe that more in just a little bit. And something that turned out to be exceptionally important, because there is now a debate in the literature based on my paper and the one other paper on this topic, which arrived at absolutely opposite conclusions. And I'm going to argue that a lot of this has to do with our choice about what regions we masked out in this map. So, and that is that I insist that if we're trying to understand the CGM of galaxies, right, the circumgalactic medium of galaxies, we have to be extremely cautious of contamination from the intra-group or intra-cluster mediums, right? And this is the reason for this. When you're in a galactic halo, right, your gravitational potential well is nowhere near as deep as in a group or a cluster, right? Therefore, the virial temperatures are significantly lower. Now, the temperature that your gas is at will dictate the dominant cooling channel, right? So our galaxies live in sort of this temperature regime. So most of their emission is coming from lines, right? So this is line emission dominated, which is proportional to gas density to the first power, okay? If you end up in groups or clusters, you're dominated by Bremsstrahlung emission, okay? So first of all, your virial temperature is higher. Second of all, this emission is proportional to density squared, okay? And so if you have even one group or cluster in your sample, it's very easy for that signal to dominate over all of the contribution from the galaxies. And so this is why my group insisted that we would really like to mask out all the groups and clusters very generously before we proceed with our analysis. And that's what we did. This is our SDSS galaxy sample, sort of a distribution of properties. I will note, so basically we split the stack into low mass and high mass. This is basically following Ben Oppenheimer's 2020 choices, just so there's already a detailed theory paper about this, and we're just gonna make the same choices. So low mass and high mass. Then within each mass stack, we rank order the galaxies by specific star formation rate. We call the top third star forming, the bottom third quiescent, and the middle third we honestly throw out, because we wanted to have a very clean break between these two populations of galaxies, looking at star forming galaxies on the one hand and truly deeply quenched galaxies on the other hand, okay? So also we applied redshift cuts. If a galaxy is too close, there's a solid chance that you just have an individual detection. Again, this will dominate the stack. Also, it's probably been studied before. If you go to too high redshifts, the noise is significantly larger than the signal. And so adding it, you're mostly adding noise. So this is how we constructed our sample. And this is our preliminary, the first result, right? If you just look at the stacked images, and this is in arc seconds, this is not physical coordinates, but the first thing you can see is that the high mass galaxies are more luminous than the low mass galaxies. The second thing you'll see is that the star forming galaxies are more luminous than the quenched galaxies. Okay, this is our first order result. Now we're going to compare this to the simulation. So how were these mocks prepared? You start with your simulation. You look around the galaxies in the simulation. You take something like 3 virial radii of the galaxy. You cut out that much information from the simulation box. Then you look down a cylinder at the galaxy and compute the projected emission. Okay. Now again, the projected emission of what? You can compute exactly how much X-ray flux will come from those simulated gas particles because from the simulation, you know the density, you know the temperature, you know the metallicity of every single gas particle. So you can use a code like PyXim, which is what was in this case. So you use PyXim to simulate all the X-ray photons, and then you're going to pass it through a mock observation. So you're going to tell the pipeline, I have an instrument that has this effective area, which is how many photons the detector can capture at a given energy range. This is the effective area of my instrument. This is how long I'm going to observe it for. This is how far this galaxy is, so you can compute your luminosity distance and all of that. And you end up with images just like this, right? This is what the computer tells you you would see if you had an instrument that could observe these simulated galaxies. And then we stack them in exactly the same way, and you end up with this many galaxies in each of the stacks. Now, there's one more thing that the simulations cannot capture directly, and that is X-ray binaries. Okay, so galaxies contain X-ray binaries. They live preferentially in the centers of galaxies. They fill the star-forming regions of the galaxy because they are just dead stars at the end of the day. But if you're going as far out as the virial radius, this is still relatively central, right? Nevertheless, you have these unresolved point sources. I mean, you may be lucky enough to find X-ray binaries within the Milky Way, a couple of nearby galaxies in the local volume. If we're going to a redshift of 0.1, you're not going to resolve your individual X-ray binaries. But because E Rosita, despite its resolution being better than ROSA, it still has a somewhat broad PSF. So if you have X-ray photons coming from the center that you haven't masked out, the PSF will smear them out to a larger radius. And so they will also contribute to your signal. So what we did is we looked at studies that actually did resolve X-ray binaries in nearby galaxies and created these clean little scaling relations. So the X-ray binary emission actually correlates to the stellar mass and star formation rates of the galaxy. Now, those two things are numbers that we do have. And so we use these scaling relations to predict how much X-ray binary emission we expect for each galaxy. And then we convolve that with the E Rosita PSF to essentially get a profile for the X-ray binary emission. Because at the end of the day, the power of our study is that we're able to do spatially resolved analyses of the X-ray CGM for the first time. But before I go there, let me start out with just the stellar mass X-ray luminosity relation, this is one of the first two measurements of this in the field with the opposite results, which is exciting, right? So, one caveat I feel the need to mention. So here you'll see green is TNG, orange is Eagle. And when you stack images, what you see is the mean signal, the average, yeah? Here you'll see there's a lot of scatter at any stellar mass for the LX of any of the galaxies in the simulation. So when you take an average, you're going to see those solid lines, right? Whereas the dashed lines show the median distribution, okay? And so what I'm telling you is just, even though stacking allows us to probe not the biggest and brightest galaxies, we're still going to be biased towards the more luminous galaxies at any stellar mass. That is something we unfortunately cannot work around. That said, this is why it's important to do this mock imaging, because when you have your mock stacks, they also will show you the mean image. And then you can do an apples to apples comparison to your observations. That said, here we are. Blue show the star-forming galaxies. Red are the quenched quiescent galaxies. The crosses are my observations. The X's are TNG, and the hexagons are Eagle, okay? So the first result is that even after correcting for X-ray binary emission, we are convinced that star-forming galaxies have more luminous X-ray CGMs than their quiescent counterparts, okay? That is result number one. Result number two is that the LX-M star scaling relation in the observations seems to evolve much more slowly than in at least these two simulations. I heard some whispers that Romulus might be different. Please show me. But for now, right, I mean, that would be so exciting. But for now, right, what you see is like you have this kind of slope for Eagle and TNG for both the star-forming and the quiescent populations. And the observations are just much more calm. They're just less sensitive to the stellar mass. So this is the sort of thing that we would like to you know, resolve in future iterations of our galaxy evolution models. And as I said, there's a humongous difference between our conclusion and that of the team at MPE, which is the team that really operates eROSITA, because they also published a study about the CGM in stacks of galaxies, but they concluded that quiescent galaxies are more luminous, which, if you will notice, is exactly the opposite of what I said. And so, of course, I had to explain why we came to opposite conclusions with the same data. And I did a variety of tests. I looked at everything that we did differently, and there's two big differences that contributed to this. One is, so they made the choice to not mask out a group or galaxy if it was in the same redshift range as the galaxy, sorry, not to mask out a group or cluster if it was in the same redshift range as the galaxy sample that they had. In other words, they said, if a galaxy we have is a member of a group or a cluster, we would like to know about its group or cluster environment. Whereas I said no, right? And so the reason this is going to have this is going to affect bias your measurement is that you're going to have group galaxies which are preferentially more quenched, right? Galaxies in groups and clusters are preferentially more quenched than galaxies in the field. So the things that they did not mask out will only contribute to the Q stack, not the SF, not the star forming stack. So that's thing number one. Thing number two is that they actually integrated all the way out to 300 kiloparsecs, whereas I integrate out to 100 kiloparsecs. Now, if you look at the simulations, you will see that you really don't expect the CGM to go much further than 100 kiloparsecs. If you go all the way out to 300 kiloparsecs, especially if you're including groups and clusters, you're really capturing the intragroup and the intracluster medium, okay? So you are capturing something, but at least for, like, I would say, my choice is that that is not what I would want to know as the CGM. I'm interested in what is happening within the galaxy halo. So when you see these two papers side by side and you're like, why do they have opposite results? This is why. Okay, they have included group members, group and cluster members, and they've integrated out so far that you're really capturing the large scale environment rather than the CGM. Now, last thing, and this is honestly my favorite part about this paper. This is the thing that actually hasn't been done before, which is you have a profile, a surface brightness profile of the hot CGM for the first time, and you can compare this to your observations. Sorry, to your simulations. So first, you have just the raw observations are shown here in black. As before, TNG predictions are shown in green and Eagle is orange. You can remove the contribution from the low mass X-ray binaries. This is a population that correlates with the stellar mass of the galaxies, which is known pretty well. Additionally, you can correct for the high mass X-ray binaries. This depends on the star formation rate, which anybody who's tried to measure star formation rates in galaxies, especially using only optical data, will know the uncertainties are rather large. So that's why I showed the purple and the blue lines separately. You know, take the blue information with a little bit of caution. Nevertheless, this is as good as we can do at the moment, right? And there's really a lot of information right here. So first of all, the simulations actually surprisingly, I shouldn't say surprisingly, the simulations don't do a bad job, despite the fact that they weren't designed to reproduce the CGM. There really weren't these observations available when Eagle or TNG were calibrated. So it is promising that to first order, the feedback prescriptions are producing CGMs that look something like like what we observed. That said, so you will notice that in these quenched galaxies, so I like to talk about the quenched galaxies first because, especially in the simulations, there's no star formation happening here for quite a long time. And so everything that you see is the effect of AGN feedback models. And so what you'll see is in the low mass stack, the simulations lie slightly below the observations. In the high mass stack, Eagle performs a little bit. Eagle actually agrees fairly well with the simulations, whereas TNG lies significantly below. And so, so what this is telling me, right, is that it could come from one of two things. Either you are removing too much gas, right, and therefore your surface brightness is lower, or you're not enriching your gas sufficiently, you're not chemically enriching your gas enough. And since the emission is coming from line emission, that could be a possibility. That could be why you don't have enough X-ray flux. That said, to me, it seems like if this were an issue of chemical enrichment, that seems harder to, it seems harder to explain why the discrepancy varies with stellar mass. Because if the issue is actually with, sorry, just one moment, I'm going to rewind. If the discrepancy has to do with whether your AGN feedback is over or under efficient, there are actually two factors to this equation. There is how efficient your so the fact that the function of stellar mass is different is telling me that this has something to do with halo loss and the gravitational potential in a way that, at least to me, it's not obvious how chemical enrichment, although I could be wrong, so please let me know. And lastly, I will note that for the star-forming galaxies, I think it's particularly exciting that there was no way I could get rid of that excess at large radii. So the observations consistently produce an sort of more extended envelope of hot CGM in low mass star-forming galaxies. I think this is really exciting. I think this possibly suggests that feedback associated with star formation processes is more powerful in the real universe than we allow for in these simulations. And so it could be ejecting little blobs of gas, which would leave an asymmetric signal in any one galaxy. But since I'm stacking hundreds of galaxies at a time, you could end up on average with something like an extended envelope signature. So that's where I am so far. Basically, at the end of the day, more massive star-forming galaxies have brighter CGMs. There are some agreements, but also some significant disagreements with simulations. And I think these give us hints about how to develop galaxy evolution models going forward. And I would love to see what Romulus has to say about this. Thank you.
Thank you very much. Do we have questions for Urmila? I will give Si Jing the first question.
This is Si Jing Shen. It's very interesting results, and thanks for the great talk. Yeah, so can you just go back to the slides you have between the star formation? Yeah, so the more extended X-ray emissions for star-forming galaxies compared to, in observations compared to simulations. Mm-hmm. And you mentioned that it could be that the feedback is supposed to be stronger, but it could also might be because of the cooling in the CGM. So maybe the simulation can be overmixed, as Ben already mentioned in his talk, so that the cooling rate is a bit higher. Whereas if you might look at the higher resolution simulation in the CGM, maybe you will see a more separation between the cold phase and the hot phase. Could that be one of the reasons? I'm just curious. Like if you're looking into like simulations where the CGM is actually better refined, you will see more sort of differences there. Or yeah,
that's an excellent point, and you're right. Gas clumping will always increase the luminosity in the X-ray.
Right.
So this is something that I wasn't able to look at in this study because to create a large enough statistical sample, we had to work with just, for example, TNG is a good candidate because they do resolution tests. Mm-hmm. But to get enough galaxies, I had to work with illustrious 100, TNG 100.
Okay.
So
if you look at 50 or even more zoom-in simulations, I wonder if you would see
I think that's an excellent idea.
Oh, okay. All right. Go ahead, Arif. I see you want to comment on that question.
Yeah. Hi. I just wanted to drop in a quick comment that these profiles and the feedback responses relative to star formation, non-star formation, is actually just as sensitive to whether there are metals and metal cooling is included in the simulations. It actually works in a completely counterintuitive fashion. The fact AGN feedback is being modeled in somewhat rudimentary fashion leads to overheating of the gas when there is extra cooling going on. So whether that's extra cooling due to higher density of gas or whether there is metal cooling allowed, all of this tends to go in exactly the opposite way. I'll show a picture, a slide in my presentation that might illustrate this a little better.
Mm-hmm. That's very exciting. Yeah, as I said, when you see a discrepancy like this, it is going to be some combination of these two factors, your chemical enrichment model, and I guess associated your metal cooling, which relates to your, how well have you enriched the gas, how well are you modeling the cooling because of that enrichment, and then what is the density of the gas. You're absolutely correct. These things all interplay, and I would love to see future studies that can disentangle those effects.
Okay, Ben, did you want to go ahead and ask a question?
Sure. Yeah, Ben Keller, coughing guy again. Like it's been said already, this is awesome. Really, really cool results. I was curious, you mentioned this sort of degeneracy between the density of the CGM and the metallicity of the CGM. Have you looked at the first set of results you showed between with the increase in X-ray luminosity for for quiescent versus star-forming galaxies? Do you know if that's because in one case you're pumping more metals in, or is it that the CGM is just denser?
Yeah, this is a good question. So something that's interesting and not obvious, I think, about X-ray observations is that so if your simulated galaxy has a metallicity of, say, 0.2 solar versus 0.5 solar, that can create a very different signal in your mocks. However, if your observed galaxy has a metallicity of 0.2 versus 0.5, because of just the way that the Chandra response, or sorry, the response function of most of these telescopes, including ERA-Zeta, works, it'll actually produce the same luminosity. So you can test this. There's the software that we recommend in the X-ray community is called PIMS, like the alcohol. People love alcoholic acronyms. But yeah, so if you go to PIMS, you can play around with different assumptions for how enriched your observed galaxy is and how that affects the observed flux. And you will see that this is a very small effect. It's like a few percent level. So which is actually kind of nice, because that means that our observations are not metallicity sensitive, but your simulations are metallicity sensitive. And so you can actually test whether metallicity is the culprit in your simulations, because the observations won't change regardless.
Okay, and with that, let's thank Urmila again. We should move on. Okay, and our next speaker is Davide De Cataldo.
And I'd like to talk about some of the highlights of my ongoing research on Lyman alpha radiative transfer. I want to focus in particular in explaining the origin of extended Lyman alpha halos that we observe both at high and low redshift. And I'll do this by post-processing numerical simulation. So let's have a look. Let's start with a very brief introduction about the basics. So Lyman alpha is the line following the transition in hydrogen from the first excited level to the ground level. So it's not a surprise that this line is very important, because hydrogen, of course, is the most abundant element. And since it depends from many of the properties of the gas, like its density, the temperature, the velocity, so it can be a very powerful tool to understand the properties and the structure of our galaxy. The problem is that to study this line, we have to understand properly how the line is produced and how it is scattered around the interstellar medium. Indeed, this line is resonance. It means that the photon are scattering a lot around the galaxy. So it's not immediate to relate the observed light to the properties of the galaxy. So it's important to mention what are the main mechanisms responsible for hydrogen to be in excited state, because if we want to observe this line, we need firstly to understand why hydrogen is found in an excited state. And the two main mechanisms are the recombination following the ionization of hydrogen. So in an ionized region, we have the recombination in an excited state that can be followed by Lyman alpha emission. Another mechanism instead is collisional ionization, collisional excitation. That happens naturally when the gas is hot enough, so we have collision that excite the hydrogen. So Lyman alpha extended halos are observed in many galaxies, and in the last decades we have plenty of observations. In particular, I'm showing here the observations from the Mule survey from redshift 3 to 6, but there are a lot of examples. This is just one. And as you can see from the lower plot, the typical extension is up to 50 kiloparsec in this case, but there are observations also halos with a diameter of 200 kiloparsecs. So our goal here is to understand first what is the energy source that is responsible for the emission of Lyman alpha, and then how can we explain why these halos are so extended. Because in observation, we can see that the extension is actually larger than the extension of the UV emission. So we can imagine that this is due to the scattering nature of this line. So let's go into the details of my work, starting first with an overview of the machinery. I will go in the following slides into the details of each of these steps. So you can start with your favorite SPH simulation. In particular, I am analyzing ACE2K and Romulus. From these, we proceed interpolating over a grid, because our code for the radiative transfer of Lyman alpha works on a grid. So we have to interpolate the SPH data into a grid. And to do this without losing information, we opt for a nested grid. In this way, we don't lose information in the central region, which is the most dense and the most interesting, having a very high resolution in the central part. After this, we post-process with Ramses RT, which is how I named my version of Ramses RT, with the implementation of a chemical network with Chrome. In this way, we can get more accurate abundances of the chemical species, because of course, it's very important to understand what is the ionized fraction of hydrogen if you want to predict correctly the Lyman alpha emission. Finally, we proceed with the post-processing with Mocalata, which is a Lyman alpha radiative transfer code. So let's go a bit into the detail of each of these steps. So in this example, I start with the simulation ACE2K, which is a zoom-in simulation of a Milky Way type galaxy. The resolution is quite good. It's like 10 to the 5 solar masses in dark matter and around 10 to the 4 in gas mass. And it's featuring a lot of nice mechanisms, like we have a cooling, which is done through a non-equilibrium network. So once I have this simulation, I want to post-process it first with an RT code to have a proper definition of the structure in terms of chemical abundances. And I do this with my version of Ramses RT and Chrome. So Ramses RT takes care of the propagation of photons, while Chrome takes care of the chemical abundances in the gas. I choose to use 10 photon beams, which is the best we can do to account for all the chemical reactions in the simulation. And in particular, I have 9 chemical species, which are all the possible combinations that we can have with hydrogen and helium. So with only 9 chemical species, we actually end up with 53 reactions, which is quite a big number to handle on the fly in a radiative transfer simulation. After this, we can proceed with the post-processing with the radiative transfer for the Lyman alpha line. And for this, we use the code Mocalata. This code is taking into account many mechanisms. For example, we have to consider the thermal broadening of the line, the Doppler shift due to the fact that the gas emitting the line has an intrinsic velocity. So we have also to take into account that. And very fundamental is the accounting of dust absorption. Dust is very important because it, as much as hydrogen, is responsible for absorption and scattering of the line. And this term is usually scaled with metallicity because we expect dust grains to be formed by metals. The approach is done with in a stochastic way with the Monte Carlo implementation. This means that we don't take into account, of course, for all the photons, but we want to actually draw with the probabilistic approach the photon, the location, the velocity of the absorbed atom considering a velocity distribution, the travel distance by each photon, and finally also the scattering direction, which is not isotropic, but we have a phase function describing the direction of the emitted photon. So putting all this together, now we can finally apply everything to our simulation, which in this case is ARIS-2K. So starting from the intrinsic emission, as I mentioned at the very beginning, we have a collision term responsible for the excitation of hydrogen and the recombination term. So we can see immediately that basically recombination doesn't count almost anything. And this is actually not a surprise because if you consider how the two terms evolve with temperature, we have the recombination term just declining with temperature, while the collisional term peaks at a temperature of 10 to the 4, 10 to the 5. And it happens that most of the gas in the CGM of our simulation is found at that temperature. This is very interesting by itself as a result. And indeed, we decided to explore a bit more what is the origin of this cold gas found in the CGM. And in the left plot, you can see how the cold gas below, in this case, 3 to 10 to the 4 K, is found in many small clumps. By tracking back the SPH particles, we can see that actually most of the gas, like 65–75% of the cold gas in the CGM, doesn't come from any other location. It's just gas found in the CGM and cooling down. This is really interesting because there are many ongoing studies to understand how gas can actually cool from very high temperature to low temperature in the CGM. It's interesting also to see that there is a small component of the CGM which is cooling, for example, in outflow or in inflowing gas. So I think this is very interesting, and each of these terms deserve like a better analysis. Oops. The cooling itself in the CGM is not actually crazy to explain because running the temperature evolution with the cooling function in ARIS-2K, we can see that the gas which is dense enough, let's say above 10 to the -2 particles per centimeter cube, can reasonably cool in a time scale of 10 megayears at most. So actually, it's totally reasonable that gas dense enough can cool in the CGM. And to actually get this result, you need a simulation which has a high resolution, high enough to probe actually the gas with a high density. Arrived to this point, we can finally apply the radiative transfer with Mokalata. And here I show the collisional term, since we just saw that the recombination term doesn't count much, compared to the final result after the radiative transfer of the Lyman alpha line. And so as a main point here, I underlined that of course, you have a lower flux, showing the fact that dust absorption is very important when making a radiative transfer calculation for Lyman alpha. We also see that the extension in space is larger after the radiative transfer, and this is due to the fact that the Lyman alpha is scattering around the galaxy before reaching the observer, and so we can clearly see that this can explain why we observe actually this extended feature of halos. Finally, I also point out that we can manage to reproduce the typical double peak in the spectrum of Lyman alpha line that we usually see in observations. But for this, you really need a good resolution in the simulation, because if you you cannot resolve the dense clumps in the disk of the gas, then you don't manage of the Lyman alpha line. So just to sum up what are the main results, we developed this machinery for producing Lyman alpha emission starting from any SPH simulation. We can reproduce the extended Lyman alpha halo that we observe we have in observations by processing a simulation with a good resolution. And finally, we also track a bit what is the origin of this cold gas 10 to the 4 K in the CGM, and found out that the main mechanism is actually cooling in situ in the CGM. Thank you for your attention.
Questions for Davide? Go ahead, Andrew.
Hi, Andrew Ponson. I'm going to sound a bit like a broken record because it's a bit related to what I was saying to Alex, and it's also related to what you were just saying about resolution. I mean, the one person who's really studied cooling in situ is Filippo Fraternelli, I think, who found you need to go down sort of 2 parsec resolution to get that right. So, I mean, should we regard any results from this as just being completely unconverged at the moment, or is there something that we can take away that's okay?
So what I found is that with this resolution, you get a lot of H2, but of course, we could actually try to push it farther and to see what we get. In the center here, we get actually a parsec resolution. So if you mention 2 parsec as a reasonable scale for convergence, I think we are almost there. Even, yeah, I think some region in the center has like sub-parsec resolution in this kind of simulation.
But presumably you need it through the CGM, and that's the really scary. That's the really scary bit.
Yeah, that's true. In the CGM, we have here 110 parsecs.
So we all need to make subgrid models of the CGM, basically, now, as well as subgrid models of the ISM. Tom says yep.
Okay, any other questions for Davide, either on Zoom or in the room? Okay, if not, let's thank Davide again. And next up is Alice Shimek.
Hi, so this is a bit of a different talk because I come from a bit of an in-between between observations and simulations, because I am modeling observations for a telescope project, which is the ATLAS project. Oh, is it working? Ah, wrong button, sorry. So what is ATLAS? ATLAS is the concept for a 50-meter single dish sub-millimeter telescope, which will cover approximately the same bands as ALMA, so it's supposed to work in good synergy with it. And because it's a single dish and not an interferometer, it's tuned to detect extended and faint structures in the universe. So there are many science drivers for ATLAS, but in my PhD, I'm mostly focusing on the hidden CGM and the spatially resolved SZ effect, and I'm in this talk just focusing on the CGM. So what do we mean when we say hidden CGM? It's been said before. We find a lot of cold gas recently in the CGM of high-Z galaxies, high redshift galaxies and quasars, and also in simulations when we increase the resolution, we find more and more cold gas in the CGM actually. So this is a component that it would be interesting to study. So if we have ATLAS, which captures these diffuse structures, we can actually see this gas. Here we can see a simulation. So this is one of the main motivations for ATLAS. This is a galaxy at redshift 0, and it's put into what's basically a simulator for a telescope. It's first with a modified version for the ALMA simulator, which is kind of a model version of ATLAS, and then we have an ACA simulator and then ALMA. All 3 have the same observing time. What you can see immediately is that for ACA and ALMA, we filter out almost all the emission from the galaxy itself, so we don't really see any structure. This is first of all because it's an interferometer, but also because the point of view is quite small. So we need a lot of different pointings to capture the whole galaxy and can't really use the observing time. Well, if we have a big dish where you don't need as many pointings, we can actually have deeper observations and recover the CGM of the galaxy. So with all that in mind, my project goals are I'm using cosmological zoom in simulations to model the emission in sub-millimeter and far infrared lines. I'm basing my models on previous models, but these models have mostly focused, first of all, on lower resolution simulations and also on the ISM and not on the CGM. And within my work, I'm also investigating how different modeling approaches actually affecting the resulting emission in the sub-millimeter. So I'm using this simulation at the moment. This is the Ponos simulation run with gasoline. It's the progenitor of a massive galaxy undergoing a merger, which you can see. Nope, that's wrong. The quite chaotic system at high redshift. The mass resolution is quite good, so with around 900 solar masses, which makes it quite nice because we can kind of have to resolve GMCs where you have, of course, molecular lines in the sub-millimeter. To kind of distinguish where the emission I'm modeling comes from, I'm separating the galaxy in different components of the entire halo, which is just everything out to the virial radius, then the main disk and the merger components, and then removing the main disk and the mergers, we have the pure CGM, which you can quite nicely see here. As I said, I'm testing different models, and these are the three main models I kind of use. The first one is a simple model where basically I take exactly what the simulation is giving me, put a cloudy grid on it, and then see what the emission maps look like and what the luminosities look like. The second model is the multi-phase model where I divide the gas into a dense component and a diffuse component. The diffuse component, again, I use just the simulation values, but for the dense or GMC components, I apply subgrid density profiles, and I'm testing a few of them just to see what difference does it make. And then the third model, which is the RT model, which I'm working on with Davide, which is a work in progress still, where we do radiative transfer, take the radiation fields of all the particles, again, apply a cloudy grid, and then see what comes out. And I'm modeling a few different, really prominent sub-millimeter lines, which is C2, which traces PDR regions and atomic gas, C1 and CO, which trace molecular gas, and then O3, which traces warm diffuse gas, just to see what difference it makes to all the different phases. Because a lot of also previous studies, they only look at C2, for example, and say, oh, this doesn't change much when you change this, but maybe it changes in a different line. So that's also quite interesting. Here in detail, the different density profiles I use, and you can see they have quite different shapes, especially the logotropic and polar profile. You can see the beautiful singularities in the center, which cause a few problems, which I will mention a bit later. My cloudy grids, they're all multidimensional because I can't do a single cloudy grid for every particle, especially at Ponos, which is so many particles. So I make a grid using the density, temperature, and metallicity, but also for the dense phase models, I use the pressure and the mass of the dense particles. And here you can see how I really simply define what is dense and what is diffuse. So if we have above a certain density and below a certain temperature, I define it as this is dense and treat it with a subgrid model, while the rest is diffuse and doesn't get a subgrid model. So everything in orange here is dense, the rest in gray is diffuse. All the models, so simple model and multi-phase model, have a uniform radiation field, which we will change with the RT, which is scaled with the star formation rate density of the main disk with a spectra in a shape similar to the Milky Way. I also include the self-consistent dust depletion, which is scaled with the metallicity, CMB radiation scaled with the redshift, because high redshift CMB is not, you can neglect it, and also cosmic rays, which are also scaled with the star formation rate density of the main disk. Also to actually see how different what difference the multi-phase model does, the diffuse model, or they use the same as the simple model, just that we only change the dense part. So here's, I said I model a few different lines, but these is one of the most prominent lines in the sub-millimeter far infrared. So you can see the maps for all the different models in the C2, and you can see immediately we have quite an extended emission. So this is out to the real radius. So it's not only in the main disk and the merger, it's also in the CGM, which is really nice. Actually, depending on the model, we get up to 10% of the total emission that comes just from the CGM component. They all look quite similar, of course, but they vary a bit from each other. but also they vary in just the total luminosities and also how much percentage what component of the galaxy actually contributes. What we also found is that the C2 and the O3 actually varies quite little if we vary between the models, while of course the atomic traces like C1 and CO, they vary far more because they depend far more on the subgrid models. And as I said before, power law logotropic profile have this neat singularity in the center. So you actually have to be you kind of manually have to put in the maximum density of the center yourself. Because I played around with it, you can just change the total luminosity like by 2-3 orders of magnitudes if you just move it a bit. So this can actually create a bias in your modeling that you say, oh, this is unrealistic, so move it a bit because we want to be like observations. So this is something that is quite important because these density profiles are really popular in modeling. Here a bit more detail, again, here are different models as a function of different galaxy properties. Here we see the high density region and low temperature region, which is where the subgrid models actually affect something. And we can see they are different from each other, which is mostly due to in the C2, we trace PDR regions. So when we look at the density profiles, how much regions would be actually PDR regions, and then Cloudy calculates how much emission we would get from them. And depending on what model we actually use, we can get, again, different contributions. Of course, the main part, you can see here, it's dominated by the disk and the merger components, but even if we remove that, we get between 4 and 10% of the total emission just from the CGM. We also tested it, of course, if it makes sense. Here's it as a function of the staff emission rate, which is a common C2 plot, basically. And in the back, you can see here the different models for the halo, the disk, and the CGM. And in the background, there are observations at similar redshifts. And we are quite good in the scatter, which is quite nice. Even if we just have the super simple model where we don't really do anything, we are quite in the scatter. But it has to be pointed out that here the CGM, the luminosity and the star formation rate are not insignificant. So if you use, for example, a star formation tracer from UV, but then you don't actually calculate a lot of your emission in the submillimeter could come from the CGM, you could get biased results. Not the end, a first look at the last model. Again, I'm working with Davide on this quite hard. We use Ramses and Chrome in post-processing, and we also include a uniform UVB, which has been included in any of the sub-millimeter studies that I've seen that try to model the emission, because they look at the ISM. UVB background is maybe not so important, but for the CGM, it's quite important. And we actually tested it, and it makes a huge difference. We can see here it's the H2 fraction for the whole halo, and we can see extended H2 structures actually, and they are much more prominent if we don't have UVB. So we see that it's quite important to actually include it. But now, last week it finished the run, so we have now the radiation at 10 different bands, and what we're now going to do is find a way to properly include this in the cloudy modeling, make the cloudy grid, and then actually see what kind of emission we get. So in conclusion, we have significant amounts of cold gas in the CGM, which you find in both observations and simulations, and we need a cool telescope like Atlas to actually observe these structures. And there are different kinds of modeling, and it's quite important to know what you're doing because you can bias your own modeling to be like the observations. Thank you.
All right, questions for Alice? I am also sort of amazed at the amount of cold gas that you guys are finding in the CGM. And I know Davide was saying that it was cooling out in situ. Was Vita's talk that also suggested that that cooling could be triggered by substructure though? Do you think this is cooling that's happening like directly out of the halo? Do you think it's like satellites are passing through and triggering cooling? Do you know what?
There've been a few studies that they try to look at actually the flows, and they start to find that when you have already cool structures, that they can cool even though they're inside of hot gas. So I think it's if you have outflows, inflows, or just cooling itself in the CGM, if they on the right regions. There are simulations that are focusing on this right now.
So as soon as you get some, it triggers more, is what you're saying. Okay. Andrew, are you going to follow up on that? Go ahead. Yes, I don't see any other hands.
Sorry, it's Andrew Ponson again. Apologies. This is really interesting. A student of mine, Teresita Suarez Noguez, did some work where she just put shocks through a CGM, and that can cool out gas as well. So it's not even substructures, but just shocks that have come from, you know, an explosive feedback event or something. But what I was really going to ask is, it's really interesting you're painting in these subgrid models. They seem really cool. But you said, quite understandably, I completely see what you're saying. You have to be careful because it can bias you. But what should we do given that? I mean, what's the correct way forward, given that it's really hard to know what to do?
I think one of the most important things is to use, which is why we're doing it. Lots of people don't do it because it's quite expensive, of course, to run. I also think that if you want to include subgrid modeling, because one of the reasons why different studies are using it is because their mass resolution is far beyond a giant molecular cloud. Well, we are kind of in the low end or below in the mass resolution, but they put in like into the massive particles, smaller subgrid particles with different density profiles. And for example, in the reason why, for example, I include two-component Gaussian profile is because observational results actually find that giant molecular cloud profiles look more similar than this, like the Plummer profile or the two-component Gaussian. So you have kind of this density profile, while in simulations they always put this in because here you can fine-tune it that it just looks like it. So I think it's, instead of trying to fine-tune it with like, oh, if we put it like this it looks more similar, we should actually maybe take a step back and see what actually makes sense. So that's my opinion on it.
Okay, and with that, let's thank Alice again. We have one more talk before the next coffee break, and that is Arif remotely.
Great. I guess I need to start. There we go. Can you see me? Can you see me and can you see the screen? Or
yep, all looks good.
Great. Yeah, so I am going to be talking about group central galaxies in Romulus sims and their near field environment, the circumgalactic medium surrounding the central galaxies. Before I go on, there are two things I just like to make note of. The credit for this work primarily goes to Lila Young, Vida Saidzadeh, who spoke earlier today, and Douglas Renahan, who I believe is in the room, and of course, Michael and Tom. And for those of you who were present at my lunch talk at CCA about a month ago or month and a half ago, some of this talk may seem like deja vu, so be warned. Okay, so I'm not going to really talk about Romulus. I expect everybody in the room is familiar with this. This is the just the standard poster that Michael developed for this simulation. We do actually have, what I do want to point out is that in addition to Romulus C, which is a zoom simulation of a 10 to the 14 solar mass system, we actually have two more zoom simulations of groups called G1 and G2 and the standard Romulus 25 cosmological volume that Vida mentioned. Some of the highlights of this work, which is now has been accepted and is available on the archive, some of the highlights of this work are, I'm trying to get rid of the images that I have. Oh, there we go. Okay, that's better. All right, so some of the highlights are that the BGGs in Romulus span a full spectrum of morphologies from spheroidal S0s all the way to disk galaxies. The disk galaxies are star forming, the spheroidals and S0s are quenched galaxies. one might be puzzled or even surprised to learn that there are central galaxies that are disky and star forming. But groups have not received very much attention over the last 20, 25 years. But there is increasing attention being devoted, and some of the more recent MUSE observations shows that indeed we do have central galaxies that are disky, star forming, and gas rich. We also looked at the kinematic profiles of these systems, and the red points that you see on the screen are showing the Romulus results. You will notice that there is and the gray points, the blue and the gold crosses are observations. You'll notice that Romulus results tend to scatter much more than the observations. That's because the observations are actually biased. Most group samples tend to be biased. They tend to target systems with elliptical or early type central galaxies. And so when you separate out spheroidals versus disk systems in Romulus, these are in the lower two panels, you see that the simulation results for spheroidal galaxies in fact agree very well with the observations, but then the rest of the scatter is due to these disky systems. We also find, as expected from the images that I showed you, that you capture the full spectrum of star formation behaviors, from star-forming galaxies that sit on the main sequence all the way to quenched galaxies. Now, this is where it gets interesting. So this is, may very well be déjà vu for those who have heard this talk before, but this is where it gets interesting. And since we are all friends in this room and it's a collaboration meeting, to some extent, I don't feel embarrassed to maybe mention this, that everything looks really good. But when you look at the trends more carefully, you find that AGN feedback in the simulations is becoming increasingly inefficient with increasing halo mass. The gas density in groups is getting more and more centrally concentrated. The X-ray luminosity is going up more than it should. The entropy profiles similarly show a much lower entropy than observations do. And this is something that I do want to highlight. But before I do, I want to point out a couple of things. That when you look at the entropy profiles for Romulus groups, you find that the shapes are actually in excellent agreement with the observations. And if you look at the temperature profiles, you find that you have a full spectrum of temperature profiles, from those that are rising towards the center and those that are dropping towards the center. If again, as you look at the entropy profiles on the left, you'll see that cool core groups and cool core and non-cool core groups do not show any difference in the shape of their entropy profiles. Groups are characterized as cool core and non-cool core based on their temperature profiles. And from that perspective, Romulus simulations do really well. Where we run into problems is that the amplitude of the entropy profiles is a factor of few too low. And this is illustrated by this plot. If you focus on the dashed purple and violet curves, those are the entropy profiles coming from Romulus simulations. The very fine dashed lines in the background are observations. The punchline here is that while the shape or the power law slope is identical to the observations, the amplitude is considerably lower. Now, this suggests that the gas is not being heated as much, and certainly this becomes a growing problem as you go towards higher and higher masses. What is really interesting here that's also worth taking note of, given some of the talks that we've had earlier today, particularly those that reference Eagle and Illustrious, is that the Eagle, Illustrious, and Simba do exactly the opposite. The solid colored lines, the bold solid colored lines, are showing entropy profiles that are coming from illustrious in this case. We have results that look at Eagle entropy profiles as well, and we find that the gas is being overheated in these systems. In other words, none of the simulations today are actually producing entropy profiles on group scale halos that are anywhere near comparable to observations. You either overheat it and create this very large entropy plateaus, or you have a very steep low entropy profiles that are factors of few too low, and therefore suggesting much more dense gas than there ought to be. All of this is suggesting that there is a critical need to go back and revisit AGN feedback and how it's being implemented. The other thing I should just mention very quickly is that simulations that have metals in them, it doesn't matter how much metals you put in, if you actually have metals in a some self-consistent fashion and allow for high temperature metal cooling, you find that the gas is overheated. So the solid bold lines correspond to models that are sort of representative of this particular type that allow for high temperature metal cooling. Romulus doesn't allow for high temperature metal cooling and finds the lower amplitude entropy profiles. And this is something that has been has been known now for almost a decade. It was first discovered by Johann Dubois and company. So this is something that I would actually encourage people to discuss. We really do need to rethink how we are modeling and or implementing AGN feedback in these simulations. Another interesting aspect, and I guess I haven't kept track of time, so how long do I have?
You've got about 2.5 minutes left.
All right, I'll do this very quickly. Vida has spoken about the CGM more broadly, so I won't do that. We are also finding rejuvenating galaxies. That means that those are galaxies that sort of end up as elliptical galaxies and then accrete gas and start rejuvenating, in this particular instance, forming a ring, a star-forming ring. These star-forming ring-like galaxies also exist in observation. So here's an example that we have been looking at via MUSE. So we see them in observations, we are observing them, we're seeing them in the simulations, and the question is, what are the key modes of gas inflow? Some possibilities are cooling flows, thermally unstable perturbations that form clouds and precipitate, settling ram pressure, or tidally stripped gas streams. So we've been looking at that, and this is what Vida has been focusing on. It's a paper that's being written up at the moment. We have been looking at gas in various cuts. Here I'm showing you a cut that's based on T cooled over T freefall. As a parameter, the color coding reflects the values of this parameter, this ratio. And the question is, why this particular parameter? Well, studies of idealized systems in galaxy clusters and groups has found that any form of perturbation, here the perturbation is due to AGN jets, but any form of perturbation that takes a medium that's in borderline thermal stability and squeezes gas in various places can actually trigger some of the perturbations to go unstable and cool out. And so you get multi-phase structure emerging just from these instabilities. Now, most of these papers have focused on AGN feedback and turbulence due to AGN jet. But in cosmological simulations, life is much more interesting. There is a wider variety of processes happening. As Vida indicated, you have satellites coming in, you have stripping going on. And so you see the structure actually present in this kind of a plot. Here's a quick example of what some of the features that we're seeing. The cyan points is actually just the classical cooling flow that's happening. It starts out, flows in, and then drops towards the center. We also have these red and yellow points. These are the existing CGM, or the medium that's present around these galaxies that's being perturbed by the satellites. as this medium is being perturbed, and Alex Liu showed a really nice slide that illustrated how this perturbation is happening. You have mixing, you have wakes that are compressing the medium, and you have thermal instability setting in these higher density features, and some of them will sort of drop down and bounce back up. These are the red ones. They are not unstable. They just sort of get squeezed and then they return back to normal. The yellow are the thermally unstable modes that actually get squeezed. Their cooling starts to increase. There's a runaway process happening, and then they start dropping out. So you have multiple such processes happening in a cosmological simulation. And then in addition, you have satellites. You have subhalos coming in with gas inside the subhalos. You have gas that's being stripped. Some of the stripped gas is mixing and becoming part of the ambient medium. Some of it is thermally unstable. And so it basically starts to precipitate. So a lot of very rich physics going on in these simulations. And, and here is a movie that's similar to what Vida showed. It's indicating the ICM gas versus the halo strip gas. And you can see a very strong spatial correlation between these two density perturbations that sort of reinforces what I described just a few minutes ago. That says, this is my last slide. What I do want to anticipate is Andrew's question. Yes, shock waves will create these perturbations. Turbulence from any mode, including AGMs, will create these perturbations. But in a cosmological simulation, at least to the extent that we can study this in Romulus, the dominant modes seem to be substructure. And finally, are we anywhere near resolving the cooling and the thermally unstable modes? No, nowhere near, not at the moment. But we can start to scratch the surface with Romulus, and so that's the interesting thing here. You should sort of view this as a window just starting to crack open. All right, I'll stop here. Thank you.
All right, I'm going to let Urmila take the first question.
This is Urmila. So which one should I start with? Okay, so I think it's really exciting how Vida's plots of the CGM entropy phase space distribution, first of all, it's phenomenal how much they look like the ICM entropy profiles that we made like 3 years ago. It almost looks so similar. The thing that I find confusing is that in the ICM community, we kept talking about how cooling, these cooling flows are triggered by perturbations in, local perturbations in entropy or temperature. But you're showing perturbations sometimes leading to cooling flows, but then sometimes leading to these other, sometimes an oscillation, sometimes just like a runaway that doesn't actually end up at the core of the CGM. So what is the difference? Like, how did you determine which of these things are associated with small versus large perturbations versus cooling flows?
Yeah, so the cooling flow is just a classical cooling flow. It's not due to any perturbation. It's just, the standard gas, unperturbed or perturbed, but mostly unperturbed, cooling and flowing inwards. So that's not a perturbed mode. The perturbations are in fact volumes of gas or gas elements that are in fact being squeezed. And it all depends on how violently they're being squeezed. If they are squeezed and pushed into nonlinear regime, then they will start to run away and precipitate out. If they are just gently squeezed and the ambient conditions are not conducive to thermal instability, and you can measure that using this T cool over T freefall parameter, then what you find is that the gas perturbation just bounces. It's this, like the standard Jeans equation kind of analysis, where if you have a balance between gravity and pressure, here it's a balance between thermal instability and pressure. If pressure wins, the perturbation bounces. If cooling wins, then the perturbation will collapse.
Okay, and I'm gonna let Michael take the last question or comment.
Hi, Arif. It's Michael Tremmel. Really great talk. Yeah, like Mila said, it's really cool that you're seeing a lot of the same things we saw in the cluster in the group environments. So my question is, so in Mila's paper, we found that AGN feedback can kind of coexist with this precipitation of cold gas in the CGM to still keep a galaxy relatively quenched, despite this cooling going on. And in fact, in Andrew's paper in 2017, we showed that continuous AGN feedback was crucial to keeping quenched galaxies quenched. So do you think, given what you said, that the AGN feedback might be underpowered at higher masses, do you think that a lot of these rejuvenated galaxies may just remain quenched with a stronger AGN feedback?
Yeah, so that's an interesting question. I'm not sure if just a stronger AGN feedback is the solution or whether it's has to do with how AGN feedback is being modeled. So, we know, for example, from work of Daniel Angeles Alcazar, that the resolution of the wind particles makes a huge difference in how that energy is distributed and how it impacts the surrounding medium. I have to think about whether it's a resolution effect, whether it's just a simple power effect. My worry is that if you jack up the power without worrying about these other issues, then we may end up in the kind of situation that Eagle and Illustris is in. We may end up with these very warm, very hot cores. And the interesting thing about that is that most of these studies first look at global integrated quantities like luminosity temperature, luminosity mass, and correlations between these variables. It turns out that those integrated properties are easy to match. What's harder to match is the detailed profiles, the detailed internal structure. And the issue that I highlighted with that entropy profile plot was the actual structure of it. So if you look at the integrated profile of Romulus, as we did in our Romulus paper, we found that, with making judicious cuts on density to try and eliminate the contamination from the interstellar medium, you get the right luminosity plot. But when we tried to do the same on group scales, we were finding that, a very large volume of the group was being cut out, which suggested that the central density core is high amplitude in density and quite extensive. And so the problem that we're seeing already sets in by about 10 to the 13 solar masses. We see it in G1 and G2 particularly. I have a feeling that Romulus, we weren't able to look at it carefully because it has a large merger towards the end. It would have been, as we talked about, it would have been kind of interesting to push it forward into time and see what would have happened in the future.
Okay. We're running about 10 minutes late for a break, so I'm going to cut it off there. Let's thank all of our speakers from this session again.